Welcome back to the enchanted bracket forest, where every twisting vine and blossoming branch represents a fundamental concept in computer science. Today, we're diving deeper into a classic algorithmic challenge, the Generate Parentheses problem. Imagine you're given a number, n, representing n pairs of parentheses. Your task is to generate all possible combinations of these parentheses, such that each combination is well-formed. What does well-formed mean? It means that for every opening parenthesis, there's a corresponding closing parenthesis, and they are correctly nested. For example, if n equals 1, the only well-formed combination is. If n equals 2, we have AND. This problem is a perfect candidate for a powerful algorithmic technique called backtracking. Backtracking is essentially a systematic way to explore all possible solutions to a problem by trying to build a solution incrementally. If a partial solution leads to a dead end or violates constraints, we backtrack and try a different path. For our parentheses problem, we'll use two key counters, open to track the number of open parentheses we've added, and close for the closing ones. The first rule is simple. We can always add an opening parenthesis as long as our open count is less than n. This ensures we don't exceed the total number of pairs we're allowed to use. The second, and crucial, rule is about adding a closing parenthesis. We can only add one if our close count is less than our open count. This rule guarantees that our parentheses are always well-formed at any point in the construction, preventing invalid sequences like. Our base case for the recursion is when both open and close counts equal n. At this point, we've successfully formed a complete, well-formed combination. Let's walk through the Java backtrack function. It typically takes parameters like result, current, open, close, and max. The result list collects all valid combinations once they are found. The current string builder is crucial for efficiently building and modifying the string of parentheses as we explore different paths. Inside the function, the first check is our base case. If open equals max and close equals max, we add current dot to string to result and return. Next, we handle adding an opening parenthesis. If open max, we append to current, recursively call backtrack with open +1, and then crucially, current.deleteCharat. This deleteCharat step is the essence of backtracking. It undoes the last choice, allowing us to explore other possibilities from the previous state. Similarly, for adding a closing parenthesis, if close open, we append, recursively call backtrack with close +1, and again, current.deleteCharat. Let's visualize this for n equals 3. We start with an empty string, open equals 0, close equals 0. We can add, so current becomes open equals 1. We recurse. We can add another, current becomes open equals 2. Recurse. Again, add, current becomes open equals 3. Now open equals max. We can't add more open parentheses. But we can add, since close open, current becomes close equals 1. Recurse. We continue this process, adding until current is. Here, open equals max and close equals max. This is a valid solution. After adding, we backtrack. The last is removed. We then explore other options from. This systematic exploration, combined with backtracking, allows us to generate all 5 valid combinations for n equals 3 and. The beauty of backtracking lies in its ability to explore a vast search space efficiently by pruning invalid paths early. It's a fundamental technique for problems involving permutations, combinations, and decision-making trees. By understanding the state and the rules for transitions, you can solve a wide array of complex problems. Keep practicing, keep exploring the enchanted bracket forest, and you'll master these algorithmic challenges in no time.